The integral of b dot ds around a closed surface is equal to 0. Something that is often overlooked and not clearly presented in textbooks is that the integral of h dot ds and the integral of m dot ds around closed surfaces are not necessarily 0. To see that, let's take the expression relating the magnetic flux density field with the magnetic field intensity and the magnetization and plug this in for B in our equation integral of B dot ds is equal to 0. So I've substituted for B, and now we can divide both sides of the equation by mu sub 0 and then rewrite this expression as the integral of h dot ds around a closed surface is equal to minus the integral around the same closed surface of m dot ds. So if we're in free space, so there's no magnetization, the integral around a closed surface of h dot ds is going to be 0. So let's look at the situation where we do have a material where the integral of h dot ds around a closed surface will not be 0. Here we have a bar magnet, and we're showing the magnetic flux density field lines that close on themselves, such that the integral of b dot ds around any closed surface is going to be 0. Inside the magnet, we have a magnetization. So the magnetization is the magnetic dipole moment per unit volume and occurs wherever we have a magnetic dipole moment, which will only be in the material. So let's take this expression and solve for h. So we can take our magnetic flux density field, divide by our permeability of free space, and then subtract off m. So the only place there will be a subtraction will be in this region right here. So this b over mu 0 here will shift down by an amount m, resulting in our profile for our magnetic field intensity. We've been saying that free currents generate magnetic field intensity, but here we see an additional source of magnetic field intensity, and that is the ends of a magnet. Let's place a Gaussian surface around the right-hand side of our magnet. So the magnet only penetrates one face of the Gaussian surface. So the integral of m dot ds around this Gaussian surface will be minus the magnetization times A, the area, and that area is the cross-sectional area of the end of the magnet. The minus sign comes about because m is pointing in the opposite direction of ds, the outward differential surface of the Gaussian surface. Let's look at the integral of h dot ds around the same Gaussian surface. So we know that it has to equal minus the integral of m dot ds around that same surface, so it has to equal m times a. And that makes sense because h is leaving the surface, so the integral of h dot ds must be a positive quantity. Now, if the bar magnet completely went through the Gaussian surface, the integral of m dot ds would be 0 because every line of m coming in comes out, and similarly the integral of h dot ds around that closed surface will be 0 because every h line that goes in comes out. If our Gaussian surface now encloses the left-hand side of the magnet, the magnetization is only leaving and coming out of this face right here, so the integral of m dot ds will be plus the value of the magnetization times the cross-sectional area of the magnet. So that would mean the integral of h dot ds around this same Gaussian surface will be minus this result, or minus m times a. And we know the integral of h dot ds has to be negative because everywhere the h field is coming into the Gaussian surface.